We expect James Webb to make great discoveries. We expect that in the vastness of space, humanity has always been curious about the mysteries of the universe. Since it began its mission in 2021, the James Webb Space Telescope has been quietly looking deep into space, taking pictures that are changing how we see our place in the cosmos. Recently, in a jaw-dropping discovery, Webb has found something incredible. This strange finding breaks the laws of physics and puzzles our understanding of reality, leaving scientists feeling uneasy. Are we alone in the universe? Or are there hidden forces waiting to be uncovered? Join us as we unravel the recent discovery made by the James Webb Space Telescope. Dark matter is like a hidden secret in the universe. It's this mysterious stuff that we can't see directly, but we know it's there because of how it pulls things with its gravity. It's kind of like a cosmic ghost hanging around and affecting everything around it. Scientists think it makes up a huge chunk of the universe, around 25%, which is a big deal considering we can't even see it. This whole dark matter thing has been puzzling scientists for a long time. Ever since this guy named Fritz Zwicky first suggested its existence back in 1933, it's weird because even though it's everywhere, we can't catch it in the act. It's like trying to catch a shadow. For a while, scientists thought the universe was slowing down. But then along came NASA's Hubble telescope, peering deep into space and discovering something mind-blowing. The universe is speeding up. About 95% of the universe is made up of this invisible duo called dark matter and dark energy. They're like the backstage crew of the universe, doing all the heavy lifting while the stars take the spotlight. Now we've got this fancy new gadget called the James Webb Space Telescope, JWST, and it's like the superhero of space gadgets. It's got this massive mirror and can zoom in on stuff far away. For scientists studying dark matter, this is like hitting the jackpot at the cosmic casino. The JWST can do this cool trick called gravitational lensing. Imagine you're looking at a distant galaxy, but there's a closer galaxy in between, bending the light from the distant one. By measuring how much the light gets bent, scientists can figure out how much dark matter is hanging around the closer galaxy. Now, some smart folk in Italy are using the JWST to study galaxies from way back, like 13 billion years ago. They're also using super fancy computer simulations to understand how the first galaxies formed. There are different ideas about what dark matter is made of. Most folks think it's this cold stuff that only interacts with gravity. But some folks think it could be warmer, with tiny bits moving around faster. It's like the difference between ice cubes and hot cocoa. The world's largest radio telescope, currently in development, sees great potential in such endeavors, believing that by pushing the boundaries of fundamental physics, we can ultimately improve our everyday lives. But that's not all. Scientists have another intriguing argument. When we look out into the visible universe, which includes Earth, the Sun, stars, and galaxies, we see stuff made up of protons, neutrons, and electrons, the building blocks of atoms. However, a mind-blowing revelation from the 20th century tells us that ordinary matter, also known as bionic matter, makes up less than 5% of the universe's mass. The rest, well, it seem to be made up of something called dark matter and another mysterious force known as dark energy, which seems to push things away from each other, countering gravity. This realization opens up a whole new realm of questions and possibilities in our quest to understand the cosmos. Most scientists are still trying to directly see dark matter. This stuff doesn't interact with regular matter and is invisible to light and other kinds of radiation. So, with our current tools, we can't spot it. But we think it's out there because it seems to affect how galaxies and groups of galaxies move because of its gravity. Let's think about a spinning spiral galaxy. Stars near the center, where most of the galaxy's matter is, should move faster than those farther out. But when we look, they all move at about the same speed. This is odd. It starts to make sense if we imagine there's this invisible mass of dark matter around the galaxy, tugging on the stars with its gravity. Some scientists think we might need to rethink how gravity works to fully understand this. Now, onto dark energy, which is even weirder. When scientists first found it, they were surprised. They thought gravity would slow down the universe's expansion over time. But when they measured it, they found it was up. It's like throwing keys up in the air and expecting them to fall back down. But instead, they shoot up toward the ceiling. Now scientists think this speeding up is because of something called quantum fluctuations in space. These fluctuations create a kind of push, making the universe expand faster and faster as time goes on. Some think this fits with an idea Albert Einstein had called the cosmological constant. He thought this constant could act like a repulsive force, pushing against gravity and keeping the universe from collapsing. But he ditched the idea when he realized the universe was expanding. However, now with dark energy, scientists are revisiting this idea, trying to understand why this mysterious force exists and what it means for the fate of the universe. In Berlin in 1915, amidst the turmoil of World War I, Albert Einstein introduced a groundbreaking theory of gravity known as general relativity that replaced Isaac Newton's long-standing ideas. By 1960, Einstein applied this new theory to the most massive object he could think of, the universe itself. His calculations led to a remarkable conclusion. The universe couldn't remain still. It had to be either expanding or contracting. This idea remained theoretical until 1929, when American astronomer Edwin Hubble made a revolutionary observation. He noticed that galaxies were drifting apart as if propelled by a colossal explosion. This discovery was later understood as evidence of the Big Bang, a moment when the universe began expanding. Essentially, Hubble observed that the space between galaxies was growing larger, implying that the universe itself was expanding. Einstein's theory accommodates various models of the universe. One possibility is that the universe stretches infinitely with no boundaries. Another possibility is that it curves back on itself like the surface of a higher dimensional sphere, creating a finite but unbounded universe. In this latter scenario, if we had powerful enough telescopes, we could theoretically see the same galaxies on opposite sides of the universe. Some scientists argue that the universe does have an edge, not in a physical sense but in terms of time and visibility. They point out that the universe began with a Big Bang approximately 13.82 billion years ago. In modern astronomy, it's whether the James Webb Space Telescope, JWST, can see the edge of the universe. The JWST, with its advanced technology, is designed to look deeper into space and further back in time than any previous telescope. It can detect the faintest and oldest light in the universe, potentially observing objects that existed just a few 100 million years after the Big Bang. While it won't be able to see the absolute edge of the universe, since the edge is continuously moving as the universe expands, it will help us understand more about the early universe's formation and evolution. When thinking about spending $1 billion on a space telescope, it's natural to ask if it can truly see that far into space. The James Webb Space Telescope is 100 times more powerful than the well-known Hubble Space Telescope. This advanced telescope can capture extremely faint infrared light from the very first galaxies in the universe. It's also designed to study planets orbiting other stars in our galaxy and check their atmospheres for signs of life. However, there's still uncertainty about what scientists will discover when they point the telescope towards the edge of the universe. To understand this, we need to know about the observable universe and the unobservable universe. The observable universe includes everything we can see or detect with all types of radiation. But there's a limit to what we can observe. The farthest light we can see comes from the cosmic microwave background, which appeared about 13.88 billion years ago. At that time, the universe was like a thick fog, making it opaque. Some scientists think that gravitational waves and neutrinos, which are tiny particles, might come from even further away. However, we can't confirm this yet because we don't have the necessary technology. Cosmologists who study the universe say that the observable universe is just a small part of a much larger reality. One of the farthest galaxies discovered by scientists is called a 2744Y1. This galaxy is notable for several reasons. It is so far away that its light takes 13 billion years to reach us. Considering the universe is estimated to be 13.8 billion years old, this means we are seeing a 2744Y1 as it was when the universe was still very young, about 650 million years old. This happens with all distant objects in space because the light from these faraway objects has traveled such a long distance to get to us. The discovery of a 2744Y1 involved 3 different telescopes: Spitzer, Chandra, and Hubble. Each of these telescopes works with different parts of the electromagnetic spectrum. Spitzer uses infrared light, Hubble uses visible and near-infrared light, and Chandra collects data using X-rays. so it explores the life cycle of massive stars culminating in supernovae, particularly focusing on superluminous supernovae like DS16C2 and M. These events are pivotal in cosmic matter and energy cycles, generating vast amounts of energy and dispersing materials that later form stars and planets. DS6C2 and M, discovered by the Dark Energy Survey, offer insights into superluminous supernovae emitting significant ultraviolet light, crucial for understanding their dynamics and the conditions leading to such powerful explosions. Moreover, recent discoveries by the James Webb Space Telescope challenge existing models of galaxy formation, hinting at a universe potentially emerging from a massive black hole in another universe connected via a hypothetical wormhole. These findings provoke profound questions about the origins and nature of our universe. The mysteries of the universe have captivated humanity since time immemorial, driving us to explore beyond the boundaries of our planet and reach for the stars. Among the most ambitious tools in our pursuit of understanding is the James Webb Space Telescope, JWST, slated to be a game-changer in the realm of astronomy. Unlike its predecessor, the Hubble Space Telescope, the JWST is specifically designed to peer deeper into space and further back in time, leveraging its advanced infrared technology to unlock the secrets of the cosmos. One of the primary objectives of the JWST is to study the formation and evolution of galaxies. By observing distant galaxies billions of light-years away, astronomers hope to piece together the timeline of cosmic evolution. These galaxies, observed as they appeared billions of years ago, offer glimpses into the early stages of galaxy formation, shedding light on how structures as vast as galaxies emerged from the primordial universe. Another key area of exploration for the JWST is the search for habitable exoplanets. With its unprecedented sensitivity to infrared light, the telescope will scrutinize the atmospheres of exoplanets orbiting distant stars, looking for chemical signatures that hint at the presence of life. This endeavor represents a significant leap forward in our quest to find other habitable worlds beyond our solar system, potentially answering one of humanity's most profound questions. Are we alone in the universe? The JWST's capabilities extend beyond conventional telescopes, allowing it to peer through cosmic dust clouds that obscure visible light. This ability is crucial for studying the birth of stars and planetary systems within our galaxy and beyond. By observing stellar nurseries where stars are born from collapsing clouds of gas and dust, scientists aim to unravel the intricate processes that govern star formation and the birth of planetary systems. In addition to its scientific objectives, the JWST is poised to challenge and refine our fundamental understanding of physics. The telescope's observations of dark matter and dark energy could provide critical insights into these enigmatic components that dominate the universe's mass and energy content. Dark matter, whose presence is inferred from its gravitational effects on visible matter, remains undetectable through conventional means. However, the JWST's ability to conduct gravitational lensing studies could offer new clues about the distribution and nature of dark matter in distant galaxies. Similarly, dark energy, a mysterious force driving the accelerated expansion of the universe, poses profound questions about the universe's ultimate fate. By observing distant supernovae and mapping the cosmic expansion history, the JWST aims to refine measurements of dark energy's influence over cosmic scales. These observations could either support existing theories or compel scientists to reconsider our understanding of the fundamental forces shaping the universe's evolution. Technologically, the JWST represents a marvel of engineering, combining a large segmented mirror with advanced cryogenic cooling systems to maintain ultra-low temperatures essential for infrared observations. Its location in space, orbiting the second Lagrange point, L2, ensures minimal interference from Earth's heat and light, maximizing the telescope's observational clarity and sensitivity. Moreover, the JWST's unprecedented resolution and sensitivity promise to revolutionize our understanding of planetary systems, from their formation to their potential for harboring life. By studying protoplanetary disks, dense regions of gas and dust surrounding young stars, the telescope will provide insights into how planetary systems, including our own solar system, came into existence. Beyond its scientific and technological implications, the JWST embodies humanity's enduring quest for knowledge and exploration. It represents a culmination of international collaboration with contributions from NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. The telescope's discoveries are expected to inspire future generations of scientists and engineers, sparking new insights and innovations that extend beyond the realm of astronomy. As we eagerly await the JWST's first light and its subsequent discoveries, we stand at the threshold of a new era in space exploration. The telescope's unprecedented capabilities promise to unveil the universe's hidden wonders, from the depths of cosmic history to the mysteries of distant worlds. Each observation and discovery made by the JWST will not only expand our scientific knowledge, but also deepen our appreciation of the vast and awe-inspiring cosmos that surrounds us.